many people think when they have working prototype that the project is finished, it's done, it's almost done, they can start selling, but this may not really be true. What do you think, Alex?
Hi, Robert. Yeah, I'm going to echo that. Developing working prototype is probably 30% of the entire journey, and making it manufacturable, working with a factory might be even more complex than making it work in the first place.
So I have got an idea. What would be the next step? What I need to do to actually create, develop, and manufacture this product? Where we go from the idea?
That's a great product. First, let's dive a little bit deeper into your idea. Let me go straight here. Here is a typical product development process. Everyone involved in hardware development probably heard about EVT, DVT, PVT process. So
I never heard. What is it?
Oh, really? Wow. Yeah, so you start with the prototypes. Let's start with you always start with the problem research. So what is the problem you're trying to solve? Technology should not be creating problems, it should be solving those. So everything starts with the demand. So someone has an urgent problem with something, and your problem should solve that. So you start with really diving deep into what problem are you trying to solve with the product. Then you go into a series of prototyping, and that might be just initial R&D, initial proof of concept, some early design. So you're trying to make it work on the table without trying to make it beautiful, without trying to make it manufacturable, just trying to make it work for that problem.
So at this is, sorry, I will always raise my hand. So this is basically the time when we would like to maybe buy some development boards, or maybe buy some existing similar solution, test what is available, maybe compare, have a look what kind of chips they use. That's what I often do.
Yes. This is the perfect time to experiment with competitor products, working with development kits. So at the early stages, you don't want to start making your custom hardware from the start. You want to really start with as minimal resources as possible, trying to make it work with minimal investment of time and money.
Okay, and I like this process because then I always have excuse to buy many toys and play with them.
Yes, yes. We've always been there. Yeah, we've all been there.
Okay, then you played with this little bit, maybe you come up with some kind of wired proof of idea or something, and then I think in the next step is like engineering prototype.
Yeah, at next phase, that's where you start making your custom PCBs. So you know your science is proven, you know what problem are you solving, you know the technology works. At this place, you start making your custom PCBs, custom enclosure. You start trying to make it look more presentable, so you can show it to someone, you maybe can take it the trade show. So this is the time when you say, I have working prototype. It's usually at this phase. I have my first engineering prototype.
Yeah, okay, we can go next. Engineering validation.
Yeah, and then once you have your fully working prototype, it's the engineering validation. So it is a time to do a lot of testing to really make sure your product meets the specification. You can do early preliminary environmental testing, FCC, UL, just to make sure your product is safe. So at the end of this, your product, you have a prototype which has been somewhat validated, and you're sure it is safe, and you can start taking. At this level, at this stage, development focus shifts to more manufacturing focus. This is the time when you start talking to contract manufacturers, and there's still a few steps left. Afterwards, next phase is DVT, or design validation test. It is a time when you start working with the factory on the design for manufacturing optimization, or DFM. When you start looking at
could we be like more specific, even engineering validation? Like,
I have a lot of slides about that.
Okay. So we will.
I have like each one of them has slides. Just want to go here super briefly, and then just go there.
Okay.
Yeah. Next phase is DVT, when you work with a factory on the design for manufacturing. You start looking at supply chain, and we can talk about it in detail once we get there. We have a full slide about this one. Then factories doing preparation for production, or PVT, and then eventually go to mass production. all in, for many products, you can expect anywhere from 1 to 2 years, if you're really good, from your initial idea to product on the shelf.
Okay, I think this is very important to highlight because that's basically also my own experience. Maybe for very simple products, it can be a couple of months, but for more complex like processor boards or something like this, it's usually like 1 year. And we even didn't talk about software development, which will continue even after mass production will start.
Yes.
Right?
Yeah, that resonates. Everyone is trying to get to Christmas. So when clients come to us and asking, "Can I make it to Christmas?" I'm saying yes, maybe next Christmas, not this one.
Okay, so let's have a closer look on this point.
Let's start with how you start. So once you're there early in a process, so how do you start? So you start with solution research. So what problem are you solving? What existing components or products already solving that problem, and how they do it? You look at the pricing. You really want to dive into competitors before you start engineering. So you want to understand who you're up against. Next phase is really critical. I think the most critical part in the entire process is to have a real clear product specification document. It's a requirement. It's a sheet outlining everything about your product that you need to know. And this is going to be a live document which is going to be evolving, but at the end, your product must comply with that PRD. I have a few templates which we can share in the next few slides. So just keep that in mind. Your PRD should be there. If I can just say what's the difference between the successful launches and the not successful ones, it's those who made it, they usually had it from the start. They had the requirements built from the start.
Mm-hmm. So basically, I would like to point out, so your company also does this complete design and manufacturing process. So basically, when you have some clients, they will deliver to you this kind of documents, and that's what you will use. And based on these documents, you then design all the boards and everything.
Good question. Everyone thinks they have for requirement document. Some of them come with idea on napkin and name it specification. Some of them have like a 20-page document describing everything. I think the truth is somewhere in between. Good PRD, it can be anywhere from a couple pages to 5-10 pages long. It shouldn't be too detailed, but it should outline everything about your product that someone from the outside must know. All the critical functionality, all the critical weight, dimension, cost, everything. So it's like your mantra when you develop, and that's what you check yourself against every time you come to a certain level.
Mm-hmm. I would like to talk about this a little bit because I remember when I used to work in companies, this specification was one of the things which delayed product development a lot. Like all the managers and salespeople, they just kept talking about specification for months or 3-4 months, and then they finally say like, oh, okay, it's done. And then after 1 month, they were like, okay, is it ready? Can we like sell it? It took 3 months just talking about specification. And also, I would like to point out what you said. It's going to keep changing because once you start selecting components, you find out maybe some peripherals requirements which were not in specification. So I really would like to talk also about this, what to do in these cases when you have questions and you need to somehow incorporate these questions in the specification. But we will talk about this, I guess, a little bit later.
Yeah. When you do your research on the solutions for similar products, you will see what are the must-haves that competitors have. It might be certain battery life, it may be certain pricing. So you do your research before you start building your specs, and then you start working on specification. Good specification can, it depends on the product size. So for something really big, it can be up to 20 pages. for something relatively small for consumer electronic product, it's usually around 5 pages. Don't try to make it perfect; it won't be in any way. So somewhere between 2 and 5 pages is a good starting point. But you have to define what are the must-haves for you, and those must-haves must be evolving. You might be adding to them. For example, temperature range, humidity are important. If you have certain functionality requests, for example, if it's a product with connectivity, you might want to include how often does it need to send data to your mobile device through Bluetooth. Important is battery life. So here, you don't think about how to get it, you think about what do you need to get.
So
solutions.
It's not going to be like super detailed. It doesn't go like into component stuff or something.
Yes.
Just the features and like really important requirements to be better than what is already available. You definitely don't want to be worse.
Yes.
You like to be better. Okay.
That is correct. What comes first? Solution comes second. Here you just define what you need to get, and you come to the how to get to the specs at the next phase when you select components and start making prototypes. Don't try to use this accelerometer or use this microprocessor in the specs, because that's a path you restrain yourself too early.
Okay, and this is the PRD, product requirement document, because you used this couple of times, so I was not sure what does it mean, product requirement document. Okay.
Yes. So one of the next phases is, this is the time when you start also experimenting with development kits. So you get those evaluation boards. My biggest recommendation, and don't quote me here, but we're highly against of using regular hobby prototype, things like Arduino or Raspberry Pis.
Can we talk about this a little bit?
Yeah,
okay,
absolutely.
So say why.
It's very early in the process. A lot of companies start with making their prototypes on Arduinos or Raspberry Pis, and they have to go and change it completely once it comes to production, because neither Arduino or Raspberry Pi are production friendly. Supply chain availability, integration into final product reliability is just not there. And if you really want to build a successful product, which is manufactured at scale, you have to use components which are production friendly. So if you want to save yourself a few months or more than a few months of time, our recommendation is always starts with evaluation boards. Some of them can even be programmed in an Arduino IDE, but it's just so much faster taking you to production if you use those more production-friendly evaluation boards.
This is interesting because, for example, when I was playing with some ideas, I often use like ESP32, and it's especially because it's wireless, it's Bluetooth, it has so much code on the internet. In a couple of hours, I can build something what if I take standard evaluation board, it can take weeks to build it. And with this kind of board, I can just put everything together in hours, really in hours. I was very surprised how easy you can create, web server on ESP32 and control or access data on the board. But then I'm very surprised it's not Arduino. So it can be ESP32, but not Arduino?
ESP32 is great. And surprisingly, it's been one of the winners of the entire shortage of semiconductors. We switched a lot of our projects to ESP32s. So you can start with development kits on ESP32s, write some code, and then just put that chip onto your own custom board and just get it working. That is a benefit. It's really easy to go from development kit on ESP32 to production, because you can use those chips. A lot of microcontrollers that are used on Arduinos and Raspberry Pis, they're just not available. That's the entire purpose why Raspberry Pi is not purchasable, because those components are not available. So if you're trying to replicate the same schematic, you're going to see the same shortage as Raspberry Pi is seen.
Okay, so why not Arduino? Because some stuff is missing, like Wi-Fi and all these other things, or?
it's just the entire approach. So Arduinos are great to make things work at the low volume, tens, sometimes hundreds of units. When you try to scale up to thousands and tens of thousands of product, first, availability for those boards will be very limited. Second,
okay. So
yes.
I understand now. So we are really talking about using Arduino in the final product, not the component.
Yes.
Okay.
Yes.
Okay.
Yes.
So that's what I would like to point out. So we don't want to use Arduino board in final product. But we can create maybe proof of concept and then take out the components from the Arduino board and build out final product based on the components which are used on the Arduino. That's okay.
Yes.
Okay.
If those components are available.
Okay, just I understand now.
Okay. If Arduino is not available at mass volume, it might mean that some of the components on Arduino board might not be available at volume.
Yeah.
So when you pick the processor from Arduino board, just keep in mind that that MCU might not be available as well.
I understand now. And that's why I don't use Raspberry Pi, because you would have to use the board. There is no way to buy the components and build it by yourself. Okay. Let's move to the
next part is very early on. You want to start thinking about the cost for the product. So when you build your prototypes, you start thinking what are the critical components, and you don't try just to lock down on specific component. You lock down on a family. So it might be a few of the chips for the Bluetooth. It might be a few battery types. It might be a few types of fans. So and you start putting together a simple document describing the cost, approximate cost for your product, and you get this table is going to evolve for sure, but you at least want to have an early idea how much the product is going to cost you. So very early on, you're just working on the table in your lab and trying to make it work, but you put those choices so you can keep your pricing in mind all the time. So when someone asks you how much your product is going to cost, once you manufacture it, you have at least a rough idea. And usually you want to have like a ballpark pricing at a different volume, 100, 1,000, 5,000 and beyond. Keeping the cost in mind is going to drive a lot of your decisions. So you're going to be more mindful if you have a table in mind.
So about this table, I see, again, I would like to point out, if someone is designing real product, they have to include everything, because I see this table is very detailed, even like magnets, textile, and all these things. Sometimes people forget about this, so it's very important, because everything is, even every dollar, if you build 1,000 pieces, $1,000. So and very often when I do this kind of calculations, I kind of ignore the 100 price for the 100 pieces, because the 1,000 is kind of there is big break, big difference. So I just don't really calculate with 100 pieces or tens of pieces, because that price is going to be very different from the production price.
That is true.
Okay. Okay, I think we can go next.
Okay, and just really briefly, once you're trying to make it work, you use 3D printers a lot. You use the rapid prototyping a lot. So at this stage, you don't try to be pretty, you're just trying to make it work. This is an example of we've been working on the wearable fan, mask with a fan. So just to keep you breathe easier. So just trying to make it work. This can be done in a matter of hours, sometimes within days. You don't spend too much time there. And on electronic side, so it's okay to use evaluation boards. It's okay to use those breadboard prototypes. It's okay to use wiring. So that's how you prototype things quickly. Don't try to make the custom board when you can just take some wires, breadboard, and just make it work.
Very often, actually, it may be even cheaper than. Sometimes I've seen some first prototypes or tens of boards actually built from boards which you can buy, because it's like super cheap comparing to trying to design it, build it, and then find out you have to redesign it because you forget something.
That is true. So yeah, custom boards comes once you already know a lot about your product, your cost, about the functionality, the chips you want to do. So you're trying to even though getting PCBAs these days is fast, you can get them sometimes in a week, sometimes in 2 weeks. It's still 2 weeks. You can get a lot done in a matter of hours if you use development kits and some wiring. So be an expert in wiring at this stage. Just make it work.
Okay.
Next part is once you know you validate your components, you remember we talked about the PRD requirement document. That is what we're trying to solve. This technical proposal is how we're solving it. So it is when we know we need our battery to work for 10 hours. At this stage, we calculate what is the battery capacity we need and what battery you might be using. So if you have, for example, another like Bluetooth chip, you might be putting a few options. So this is the how you're trying to solve it. And again, you're not trying to limit yourself. I'm going to be using this specific chip. You're giving yourself some choices, document your choices. So if you need to go back to this document a couple of months afterwards, you can have a look at what components you also evaluated like then. All clear so far?
Yeah. We can go next.
And last part about the feasibility study or about the first phase is you want to start working at some design. So just to get it very early, seeing is believing. So what we usually do when we start new projects, we start working on design very early, very rough idea about the product look. So you start with either yourself or you hire an industrial designer. And again, no need to be pretty here. You don't hire expensive companies doing that for hundreds of thousands of dollars for design work. The idea is you spend a little bit to come to the realization how it might be looking. So we usually the first step here is to come with 10, 15 sketches, different designs, to at least to have an idea about the shape. Is it going to be round? Is it going to be square? Is it going to be a cylinder? Then you narrow down to anywhere from two to four options go into next phase, and then you start picking components which are going to go in there, and at the end you have their one or two designs which are looking somewhat as a product. They are more or less renders at this phase, but you know that you integrate all those displays, all those cameras, all those memory components. This is one example of the consumer electronic products we were working on during pandemic. So very rapidly, we came from just an idea in head till the render. So, and that render was actually with actual parts built in. So at the end, we have something like this, 3D renders. So you can show to your potential investors, friends, clients, get them excited. You have something working in your lab on those evaluation boards, but you also have something to show to people, so to get them excited about the product.
Yeah, I completely agree. I remember when these softwares like Altium Designer, when they started supporting 3D views.
Yes.
Yes. That was so great because in very early stage, you could show your clients and managers how the board is going to look. Otherwise, they had to wait for months.
I completely echo that. Yeah, that was a great time, right, Robert?
yeah, exactly. Okay, and you need to be sure you will fit everything inside of this.
All right. Yes.
Okay.
All right, moving on. So you have an idea about your design, how it might be looking. So next phase is actually start working on your custom prototypes. So you remember we've seen this time frame. I'm going to be going back to this one a lot. So we start working on the custom engineering prototypes. So the core problems you're trying to solve, you validate all the components. There is no tooling, no cost optimization. Unit cost is going to be high. This is the time when the first-time customers can fully understand the product. And this is probably the best time to raise money from investors. And you're using rapid methods only to build a few prototypes, somewhere 5, 10 prototypes. And the goal here at the end is that your engineering samples meet your specification. You remember those specs we built? This is the time to meet those specs. How you usually do this one? This is a product we've been working on for quite some time. And I'm going to show you how the PCBs evolve over time. Your very first POC proof of concept might be just the wires connected to those contact plates on the device. So it can be done in a matter of couple days. Next phase is another proof of concept is when you start to making it a little bit more reliable. So your wires don't disappear from the design. You use some magnets, you use some glue, but again, it's still looking very ugly, but it's just a bit more reliable. Then you build the board in a bigger enclosure. You're not trying to miniaturize it too soon. You work with a bigger board just to validate everything. So this board work like prototype is really essential. So this is the time when all your pinpoints are accessible, test points are accessible, you can make changes, you can install jumpers. If you miniaturize it too soon, this board is going to be very hard to work with. So we usually build it like a rectangular board in a bigger enclosure. We test everything, and once it's working, we then go into the more or less final form factor. So what you see in the bottom left corner, it still works like prototype. It's taken a couple months to build. It's taken some time.
A month, yeah, okay, 3 months.
Yes,
2
or 3 months to miniaturize it, but we're using the battery, which is supposed to be used in the product. The form factor for the board is like that. We optimize position of magnets. So this is the time when we really start investing a lot of money and time into development. But you see that we validated everything before that. Before we come to this design, we already know that this chip we had previously is working flawlessly, and we can make it work.
Also, I think what is important to say, we would like to do software development in parallel with hardware development. So that's also a reason why we would like to have something working very early. And also we would like to find out all the kind of mistakes or improvements what we have to do, because there are almost always some improvements what you would like to do when you finish this very first prototype. That's also the reason maybe why it doesn't make sense to try to make very first prototype to look exactly as final product.
100%. Yeah, you work on your software development in parallel with your hardware, and your software development might be driving some changes in your hardware.
Exactly. And also it's much easier and faster actually to create these kind of big boards comparing to trying to design the very small and packed boards. And also it's cheaper, of course.
That is correct. 2-layer board, easy.
Even 4-layer board is not expensive today.
Yeah.
Okay, so the last picture.
Yeah, so your first prototype is working. You definitely find some changes. We have some wires, we have some jumpers, and then you do one more iteration to eliminate all those to make it work, and design simple enclosure. So at the end, you have a looks like prototype, which is working as a product, looking somewhat as a product, and you can go to next phase. A few tips what to expect on this phase. So, and a few recommendations is you can expect anywhere from 2 to 3 iterations of PCB design during your engineering prototyping. On all those designs, you want to add test points. This is not the time to cut them off, to try to make it too small. Have a lot of test points. They're essential at this phase because you test your product with those. Another decision to make is you want to decide whether you want to use PCB antenna or chip antenna. It's if your cost allows you to use chip antenna, that's usually the best, because you don't have to spend time on tuning the antenna. And finally, if you can make your board single-sided, that's usually best for cost. So whenever we have a chance, we use the board on which all components are on single side. That's better for manufacturability.
Yeah, because only one side is assembled, and it can save some money.
Yeah. One more example, how this was the wearable sports tracker, how we came from evaluation boards to work like prototype to another working prototype, and then to final engineering prototypes. So you add complexity gradually. You don't try to miniaturize it too soon. You work with evaluation boards, then you get custom board in a bigger form factor, you validate everything on it, and then once your schematic is proven, you go to small custom board.
This is interesting because sometimes actually I try to design even the very first board into the size what final product is going to be, because sometimes I would like to know if it's actually going to fit.
Yes.
But yeah, I think this may be also different between people what they prefer, but definitely if designing the prototype which is going to fit into final product is going to cost like much more time or money, then it's definitely probably fastest just make big simple board as quickly as possible and test everything on this board, because sometimes you would like to maybe test also more circuits, different circuits or different chips maybe, and compare the results. Maybe that could be also a reason. But very often I just wanted to point out this because very often when I'm designing something, I work with kind of almost final dimensions because the size is very often big restriction, especially when you have like standard format, and you know, management, they would like to fit their, or customers, they would like to fit their everything. So you need to tell them, no, this is not going to fit.
Yes. At some point, you want to do some, before we start working on a project, we use some preliminary placement. So we know that those components fit approximately in this form factor of a small board. But once we order first PCB, they're usually bigger. And the reason that you mentioned, you want to test multiple circuits, you want to have all the test points, you want to have all your connections. It's possible to work with a smaller board, but all the revisions, all the iterations, all those hard wire soldered jumpers are just much more painful on this small board.
Okay, we can move to the next slide.
At this phase, some wiring is acceptable. As long as it works, it's acceptable. So patch boards are also okay. Few recommendations, few actual design tips. As I mentioned, you know, it's much better to use components which can be used eventually on a product. Raspberry Pis and Arduinos are definitely not production friendly when you scale up. We recommend using pre-certified modules whenever possible. So those modules like ESP32s and others, or Nordic ones, that are pre-certified with antenna. So you save yourself quite a bit of money and time on a compliance.
This is very important.
On the FCC. Using chips from big guys like Qualcomm, MediaTek, Realtek. You know, you look at the product, like you want to build another iPhone. You look at the product, they use Qualcomm. I'm going to use Qualcomm. You get the data sheet, you start working on this one, and then you're trying to get some support. You reach Qualcomm, and they don't reply to you.
You know,
been there.
I have not really been so far, but I see many people writing about this, like they use Realtek, for example, Realtek chips, and they say like, oh, they never answer.
Yes.
Realtek is, I think, one of the chip manufacturers which I actually use I wanted to use it in one of my products, and this is what happened. Yeah. But usually then I was careful. After this happened to me, then I was careful, and I knew don't use this.
It's extremely hard to work with the big guys because they always ask for volume, and some of them might be asking for 1 million plus chips MOQ, a minimum or quantity. So if you can work with the smaller guys, it's definitely more preferred once you are small. Yeah,
I completely agree.
Moving forward, check lead times prior to selecting parts. You know, it might be it might be very intuitive, but some of us really skip this part. Before you say that, this part is great, I'm going to be using this one, check stock and lead time. Lead time might be, for some chips might be a couple years, for some might be even more than a couple years. So be careful with selecting the parts, and if you can afford using sourcing agent, to get you not just the immediate price, but the lead time and pricing if you order through regular production process. So that's usually recommended. We use sourcing agents in China and in Asia to check those parts directly with manufacturers, so we know what to expect.
Mm-hmm. I would like to point out to this also, because I have so many stories about this component selection. And I remember when I finished university, I remember this task which I've got from manager, design a board, and I was like, I found a chip and it was doing exactly what I wanted, what I needed. So they sent me 5 samples, and then I never heard about them anymore when I wanted to produce the board. And since then I was like super careful, and I have this rule, like for if I'm designing something for production, this I have to be able to buy these components from DigiKey, Mouser, or Farnell. If the chip is not there or component is not there, I don't use it, because first I would like to build the prototype very quickly, so they also need to be in stock, all the components what I use. And also very often, if it's not in DigiKey or Mouser or Farnell, then it's probably some kind of weird chip, maybe from China or somewhere, and I may not be able to actually buy.
Yeah. Actually, last year and this year, using Chinese components has become really essential. So for some components, yes, some chips are really hard to get. STM32 text instrument, extremely hard to get. So, and you have to use either chips which are from different suppliers, or using some alternatives. Had a big success with finding drop-in replacement from Chinese manufacturers for those chips. Sometimes, especially on the older product, when you cannot redesign completely and you have to be using the same board, some of the manufacturers actually supplying drop-in replacement or alternatives which can be used instead of TI parts, for example. So this has been a good time to look east.
But also be careful. You need to test these kind of components very well before you actually use them in mass production, because some of the components don't meet exactly the parameters of the original component. So I would like to point out it. Okay, so what is in the next column? Hard to get. Okay.
Yeah. These parts are right. Yeah. So ESP32s and RF32s has been a good choice for anything with a wireless. So we switched a lot of products using those chips in the last couple of years. Right?
Okay. Chinese alternatives. That's very interesting, because I was always very careful about this.
It's China has a lot of components for domestic market which are not even advertised. They have such a big domestic supply that don't even advertise. Sometimes for some products where you cannot get your TI parts or some other parts, you have to use some alternatives, and some of them are pretty good. Yes, you go for validation. Some of these guys who manufacture parts domestically in China, they might be very big manufacturers, so they have pretty substantial R&D process and quality assurance. It's hard. Their data sheets not available online. You have to go through sourcing agent. But if you are really trying to make it work, if you're really trying to make it work at scale, sometimes those are great parts, but it's not as easy as getting the parts from DigiKey, putting it in the product. Your data sheet is there, everything's there. It comes at a price, definitely.
Okay. Interesting. Next, we can go to the next.
Right, moving on. So if you want to read a little bit more about their where get components this year and where to produce, so we published an article on Forbes a couple of weeks ago. We call it diversifying your imports, manufacturing, and consumer electronic products without breaking the bank. So link is here if you want to read a little bit more about where components are manufactured. This is a great read article. Moving on, so mechanical design. So mechanical parts are expensive because they require tooling, and tooling is a fixed expense You pay regardless of your volume, whether you want to make a few, or a few dozen, or a few hundreds, or a few thousand, you pay the same tooling cost. So mechanical design must be done right. And for every product, you must be thinking about your mechanical design. If you have some mechanical background, you can do it yourself or hire someone. Just be aware that any mistake you can make in the mechanical design is going to cost you substantially, because those changes don't come cheap. So when you do your mechanical design, try to split your big structures into smaller pieces. Don't try to make those solid three-dimensional pieces. You split your structure into a few smaller pieces, which can be easily manufactured either from sheet metal, sheet plastic, or some in complex molding. And one of the big things I'm going to show you is one of the methods to actually prototype mechanical designs. So we all know 3D prints. So it's no startup cost, cheap and fast, can do any shape, but it's not as good on mechanical properties. A slightly better option is CNC machining, when you get the big bulk of plastic and you just CNC machine your part from that. It gives you a great look on the product. It's much better mechanical, it's much more robust. The downside is that it costs quite a bit, because if your product is substantial in size, it may take a couple of days to CNC machine that from the piece of plastic. One thing that we use a lot, it's called silicon mold. It's similar to injection mold, but at much lower cost. And the way you do that, you 3D print or you CNC machine your master model, like your sample, and then you put that you make a cavity in a piece of silicon. So similar to injection mold, but instead of metal, you use silicon, and then you can pour some melt plastic in those cavities. It gives you a good look. It's not as precise dimension-wise, because silicon can be fluctuating a little bit, but and those molds don't last as long. They're usually good to produce somewhere between 10 and 100 pieces, maybe. This is an example of the parts we actually have done with a silicon mold, and that has been this product, which is pretty substantial in size, with a lot of mechanical parts inside. So we used silicon mold we used 3D print and CNC machine to create master models, and then create silicon molds for those, and to produce those samples. Final results, they look amazing, and it's much cheaper than trying to CNC machine that entire batch of plastic parts from the solid piece of plastic.
Interesting. I didn't know that. So you have to find a company which will put the melted plastic there.
Yeah.
Okay.
Sometimes you can do it even in-house. We've done some experiments for something small, for something like wearable, for anything less than a smartphone size, we can do it in-house without going outside. When we work on something bigger, like this product, we usually go outside with a few vendors we work with to do this.
So there is some kind of special plastic which you somehow melt? Is there like something special how you melt it, or?
It's a similar process. Silicon mold there are a few types of. The big part is to make sure that you use proper silicon, and then you use plastic. It just must be melting at lower temperature, because when you use, for example, PVC, that just requires high temperature, which silicon might not be holding. So it's a lower temperature plastic, which might be slightly different mechanical properties, but you can get even to proper finishing, like your matte, glossy, your surface quality can be really good.
Okay. I may have a look or maybe search some videos on this topic.
Yep. All right. So you assemble modules, which are for your units. You do your assembly. You want to do this assembly in-house. You don't want to outsource this one. The engineers actually working on a product must be the one assembling this. So this is a really essential. You learn a lot about your product once you assemble it for the first time. So if you do development in-house, assemble yourself. If someone else is developing for you, company like ours, we do assembly only in-house because we want to see every small change we must make for the product to make it manufacturable. Firmware development, essential to know how much to expect firmware-wise. So you want to allocate at least 1/3 of your entire time for bring up and validation. So if it takes you, for example, 3 months to develop something, allocate at least a month to actually test it, to actually make it work. If it's taking you 6 months, 2 months will be a minimum bring up time. Don't skip that step. Don't try to say, oh, I have my PCB from manufacturer going to be ready tomorrow. Allocate at least 1/3 of the time for bring up and validation.
What kind of validation do you recommend? Because, for example, one of the validations what I really like is always run tests in environmental chambers for different temperatures. I found so many problems running at a low temperature or high temperature, which otherwise would probably appear in, I don't know, few percent of customers, but you would never find out if you only tested on your table in lab.
Yeah, that's a great question. I have a slide about that on the next phase, but I'm going to jump in there and then we're going to come back here. So once you have your engineering prototypes, you go through engineering validation test or EVT. And the test you typically run at that phase is functional. So to make sure all the functions work, power draw, power up, power sequence. Thermal is to operation at low temperature, high temperature, thermal cycling, and EMI to see how much EMI your product is actually emitting. So those are critical minimum. Sometimes you want to spend more time here and test more, but those are the minimum you want to do.
Okay. We can go back if we will be talking about it a little bit later. Then go back.
So at the end, you have final great-looking engineering prototypes.
Month 7.
Yes. It's usually, it's a real timeline, approximately 6 to 7 months to come to this stage, sometimes even longer. Sometimes if your product requires specific materials or specific something, it's okay to make it look slightly different. For example, for this part, this product was supposed to be using specific plastic, which can only be done in the during injection molding. So we skipped that material and we just used simpler plastic at this phase, knowing that we cannot get it efficiently without investing in tooling. So we got this to work at this level and then went to next phase to use proper material. If you have any software development goes in parallel. Don't spend too much time here. Don't spend too much money. Make it simple, make it work. As long as it works, it's okay. You can always iterate your software quickly. Don't try to spend more on a software than you do on a hardware.
Software can be updated, yeah.
Yes, exactly. All right, EVT, engineering validation. You have your prototypes, they're somewhat working, you're excited, you go through EVT. So you can use your first engineering prototypes to begin with. Usually you'll have to develop additional iteration of hardware during this phase. You do testing. EVT is about testing, test. And just be aware that there are no substantial changes after this phase. So whatever you do, whatever you find out must be done here. As we discussed, test to run functional, power, thermal, EMI, sometimes more. And if you do build another round of prototyping, it's usually 20 to 50 units because you have to, some of these tests must be destructive. You do power testing, you might destroy your board, you do thermal, you might damage your board. So be prepared to do a bit more units at this phase.
So we often, very first boards, what we build, usually we build like 5 to 10 boards, because from my experience, like maybe 1/3 of the boards may not work because of the low production stuff, like assembly mistakes or something like this. It even doesn't have to be anything wrong with schematic or PCB. It's just because they built 5 prototypes, there is very high chance that something wrong will be in 2 prototypes because there is wrong, I don't know, contact or something.
That is correct. Yes. So you want to have some additional units to accommodate some manufacturing defects.
Yeah. Okay. Okay.
So the question you answer at the end of your EVT is, does the product cover the requirements of your specification? If your specification classify it need to work from this temperature to this temperature, you test the entire temperature range. If you say it need to withstand some vibration, you actually test the vibration. This is the time to do all the testing against your specification. That's why it's essential to have that spec in the first place, right?
Okay, we can move to the next one.
All right, so your final boards might be looking something like this. They're pretty, they're good, they are no wires, everything. You do functional testing, so you literally go for your spec sheet and you test every single function that's on there. You might want to have some spreadsheet outlining all the testing you've done on each unit. So you want to be critical here. So you're doing testing every single feature that's in your product. Wireless testing. So if your product has some sort of wireless connectivity, you can do this early on in your own lab, in your own office, just to see the antenna performance, Bluetooth performance, data speed. So even before you go to outside party to do the formal EMI testing.
I remember Bluetooth testing, like, is it still working? It still works.
Yes. Yes. So you wanna spend as much time here as you can to make sure it's working over time. If it works for 5 minutes, it doesn't mean it's going to be working for 10 hours or 24 hours. Especially if you put it in the thermal chamber, especially if you put it in the cold chamber, or you just vibrate it and you move it around.
This is a good note, because I always, when we created these first prototypes, we had a couple of them running nonstop for as long as possible, nonstop, just being sure they are running reliable. Again, some problems may only appear once per days or weeks or even months, and it's something what should not be happening, because that's not good.
That is true. That is true. Yes. So endurance testing is critical, especially at the early stage of your R&D.
So we always took a couple of boards, put them somewhere, and they just kept running forever.
That is correct. Yeah. We also do that. It's expedited, and sometimes if you can run it at a higher temperature, let's say like 24-hour test, or actually sometimes it's even couple weeks of testing in the higher temperature, can really show you what's going to be happening with your product if you leave it there. And it's called accelerated aging, and it's really helpful.
Okay.
Okay. Moving on. Thermal. So if you can invest some money into a thermal camera, it's great. It shows you everything about your product, which you can actually see. It's the temperatures, which part of your product or your PCB gets hot. We have a lot of thermal cameras, different applications. This one is for device level testing, so we can see how hot the device runs. We have the smaller camera for the PCB testing, so really see what parts of it, whatever gets hot is going to get damaged first. So you want to know and find if that is okay. So to evaluate whether this thermal condition is appropriate.
Also, if someone doesn't have camera, I always use my fingers. But I recommend there are thermal cameras which you can use with smartphones. They are just like plug-in, and they are much cheaper than these standalone cameras. And it can be super useful, because you can notice very quickly even one very small component which is getting hot and it should not be getting hot. So you can very quickly find out there is probably something wrong with this circuit or with this component, and you need to fix it.
That is correct. And sometimes you can rent that camera for a day. So when you're just getting started, 10 years ago, we were just renting the equipment like at a small price per day, and not just buying that once we couldn't afford it. Once we get bigger, we purchase all that for our own use. Right? So at the end of EET, all your components are locked. There are no substantial changes after this phase. So everything that must be changed is changing here. If you make change, you go and test it again. So no component change after this phase. No substantial component change after this phase. You iterate as much as needed. Sometimes you take in new iteration of PCBs or enclosures. And again, no substantial changes after EVT phase. This is the end of your engineering. Then focus shifts to production. Design validation test is a time when you start talking to manufacturer. Depending on your product, how fast you are, how experienced you are, how good is your manufacturer, it can be anywhere from 3 to 8 months, sometimes even longer. So focus shifts to production of this phase. So what to expect? It's a final validation before start of production. And here you start selecting contract manufacturer. I'm going to share a few tips how to select one. You do design for manufacturing optimization with your contract manufacturer. Your electronics is final, so all the tests are completed, and you work on the software optimization if that wasn't done before that. Usually at the end of DVT, you do tooling. So all your prototypes are built with tooling. This is the time when you start investing more into your tooling, into your manufacturing, especially for plastic parts, for mechanical parts. And the question you answer at the end, does your product meet all requirements? Functional, cosmetics, and environmental. So complete validation. And again, it can be anywhere from 3 to 8 months, with 4 to 5 months being the average. Let's talk about the fun part, how to select the manufacturer for your product. Shall we?
Yeah, definitely. I think many people will be interested to know this, because even if you find one, then from my experience, we have changed number of them.
Yes. You start, it's like when you pick a school or when you pick the work, you compile the list of possible manufacturers to work with. It can be anywhere from 10 to 12 CMs to investigate. You might go to sites like Alibaba or to other Chinese if you are manufacturing in China, you have to go where they are. So a great place to find those factories is Alibaba. You get a list of 10 to 12 factories which are somewhat in a similar area. If your product is, for example, a wearable device, you want to work with the factory who is doing some wearables. If you're doing another like industrial product, work with someone who is doing industrial devices. Having the manufacturer who's done similar products before is essential, because they might have some established supply chain, which is going to be working better for your product. They might have some testing equipment for your product. So good CM can save you quite a bit of time and money because they've done it before and they can guide you. CM is your partner, not your employee. So just keep that in mind. From those 10 to 12 CMs, you look at their portfolio, you look at their references, you ask for references, ask for the products they've done. If you can, try to talk to those clients who they mentioned. Have they sold anything to North America or to Europe? Try to contact those factories, those companies, and ask them, what was your experience working with this factory? Are you satisfied? If they do allow you to see references, good factories will be glad to share the references because, the clients can say good words about you. So approximately up to 5 factories.
Sorry, I need to be a little bit negative here, because I always do this reference checking. Problem with reference checking is they will only tell you about the clients which were happy. So you never can really check the clients which were not happy. And that's a little bit tricky. And also what I think many people may have problem with is some manufacturers, they don't want to talk to you because you may be too small, but it's not always the case. I know in China, I think many companies, they will talk to you. Or what is your experience? Even if you are a small company, for example, do you think they may have problems to talk to them?
you pick the manufacturer based on your volume. So if you are small, you're not trying to talk, all manufacturers can be spread into tier 1, tier 2, tier 3, tier 4, and beyond. So if you are small, you're not trying to talk to Qualcomm with manufacturing iPhones. You pick in the factory who is approximately your size. That's why I'm saying it's essential to research companies doing similar products. So if you're doing a wearable device, have a look at some of the products they do manufacture and at small volume. So it's okay to start small, but in your communication with the factory, you must be very clear with your plan. I'm starting small. This is my plan for the first year, for the second year, and trust goes both ways. You need to trust them; they need to trust you.
Mm-hmm.
So it's a mutual process. And you can only get to know that if you actually spend some time to explore them. That's why it's essential to actually go there,
Mm-hmm.
either yourself or hire an agent to go there for you on your behalf. Nothing gives you more clarity than going to the factory, talking to their management, talking to the employees, seeing their factory. Sometimes factory might not even be there. You show up, and instead of a big factory, you might explore like a small garage. So you must go there, you must check it, you must see that in your own eyes or someone who's doing that for you before you make final decision who you're going to be working with.
What about IP safety? Can we talk a little bit about this? Because, for example,
Yes.
very often what we do is we don't manufacture everything in one company, and
Exactly.
what may happen, like we manufacture PCBs and then we deliver PCBs to the assembly house, so they don't have all the data. So you have slides on this, maybe? I don't know. Okay.
Yeah, it's a great point. So you wanna once you do your request for factories, you might be splitting. Yes, you do send your mechanical parts to this company and your electrical parts to that factory. So you get codes separately. So it's a valid alternative. Sometimes the best recommendation I can do is just pick your idea. Let us be honest. Ideas worth very little. Execution is everything. So if you have a great idea but you cannot execute, the value of your company is very little. So you want to be reasonable in how much time you spend on protecting your IP versus how much time you actually spend on manufacturing your product. So you want to have a good factory with manufacturing good products with track record. If you are successful with selecting your contract manufacturer, they're going to be with you for years and years to come. So there is no reason for them to try to copy you because they make good money on being a good partner for you. And if you don't try just to select solely on price, this is like my number one recommendation. Never select solely on price. Have a few factories in mind, like a backup option. So if you have 3 factories who are great from that choice, you keep that in mind. If something goes south with one of the factories, you can always go to the second one. Yeah.
Okay. So, and do you manufacture everything in one factory then, or how do you do that?
It depends on the product and on your financial abilities. So if you are small, if you're just getting started, working with one factory is definitely going to be a more cost-efficient option. So they're going to be using their supply chain, their resources to just put everything in place. If you are getting bigger or you have potential to be bigger, it's okay to use mechanical in one factory, electrical in another factory, and assembly in the third one. Sometimes one of our best recommendation is if you really want to be protective of your IP, don't give the final firmware or programming files to the factory. Give them something small, like just to do some functional testing. They can program that version on their own factory to test it. And when it lands in your country, you can put the final firmware on through wireless update. That is great when you're manufacturing a smart product because the majority of your IP lies in your software. So if you can keep those software files to yourself and only do final programming before you actually ship to clients, that's probably the best recommendation I can give you.
Okay, so we can move to the next one.
Right. So if you want to read a little bit more about the selecting the factory, where can you manufacture? So another reference article which is published on Forbes. Consumer electronics is done in China. More higher margin electronics is done Taiwan, Japan, and sometimes in Europe or US. If you're manufacturing something medical or aerospace or military, that can be done domestically. Wherever you are, we are in US, so we see a lot of our clients manufacture medical and aerospace products in the US.
Mm-hmm.
Let's talk about how we work with factory. So three-letter word, DFM, design for manufacturing. So you have a product, it's working great, you send to factory, and they respond with a 50 pages PDF, Excel or PDF saying, oh, this angle must be changed.
I
So
remember, yeah, I know exactly what you're talking about.
Yeah, so this is okay. This is just a few things that you must have your CFM color finished material ready. So if you say white or gray, you must have a explicit color code for that. If you say it's going to be glossy, you must specify how glossy it might be. If you specify the material, it shouldn't be just plastic. It should be plastic or this rigidity. So be very specific with a request. If you specifically request, you're going to have something you actually asked for. For mechanical engineers out there, use constant material thickness. So if your entire product is the same thickness, it's going to be better produced during molding and using draft angles. So to help your product go outside of the mold.
Mm-hmm.
So again, CM is going to drive this one. You send it to them. They give you their recommendations, and you just make changes, or they do it for you.
So this is important to point out if someone would like to, or if someone needs enclosure, for example, for their product, then it may be very useful to actually talk to someone who is designing enclosures, because there are many tips and tricks what may need to be followed to make the design of the enclosure easy to manufacture.
That is correct. A lot of things can go wrong during mechanical design, so you really want to work with someone who's done it before. That's where experience pays off. You can only learn those things after making 10 or 15 or 20 products. Even my mechanical engineers, they've been doing it for a while, for 10 plus years each, some of them for 20 years. And still, when we send files to factory always comes back with oh, can we make this change? Can we make this change? Because each factory using slightly different machines and the capabilities might be slightly different. So you always adjust for specific machine, and it's okay to make changes here. It's expected.
Okay.
Excel or PowerPoint is the language of the factory. Regardless how well you speak English or how well you can speak on the phone, none of the questions are solved on the phone, on a Zoom call. You talk Excel, you talk PowerPoint. You make a screenshot.
This is exactly what I receive from Chinese companies.
Yeah.
Picture and then columns and then some text translated from an engineer to English.
Yeah. That's how it works. Yeah. And at the end, you went through all this path with the manufacturer, you done the DFM, you pay them for tooling, which can be tens of thousands of dollars for tooling for mechanical parts. They do produce 10 to 50 units, depending on your request, sometimes more. So they're looking good. So, they're going to be, you can show them on the trade shows, you can show them to your investors. So they're good looking units, which are, we call them pre-production samples. So, and at the end, factory is starting doing some of the things like a scripting, for example, how they're going to be testing the product once it goes from production. They don't test them one by one manually. They do some scripting to actually record the events going on with the product and to automate testing procedures. Next round of
This is exactly what I kept in mind, because this is a big topic what many people forget about. If we go to mass production, you don't only design your product, you also may need to design the test to test your product. And I guess that's what we are going to talk about right now.
Yeah. At the end of DVT, there is at DVT, you still do some of the things manually, and then at the next phase, you do automatic equipment. Essential to what to test during DVT: functional, everything functional, all this, every single function in design, regardless how big or small, must be tested at this stage. Performance is how well your machine runs, how your sound is performing, how well is your wireless connectivity, everything. Climatic, so hot, cold, mid-range operation. Reliability is, as we mentioned, endurance testing, putting it for continuous operation for hours and hours, sometimes for weeks at a time. Environmental, to test that in a different air pressure, humidity. Sometimes we all know we must test it in different temperatures, but very little of us actually test our products in the high humidity, which might be even bigger risk for the product, because some of the condensation might be happening inside the device, and that might be disaster for some of the boards. So really spend time here too, and CM is gonna tell you that they can do this test, and they'll just charge you some extra to do all this testing, but this is really pays off before you invest much into manufacturing of your product.
But I would like to point out, during mass production, we don't do all these tests.
Correct. This is only happening on the design phase. You want to test everything before you start production, and then during production it's very simple, pass and fail. So yeah.
Okay.
Mechanical shock vibration. So you put it on vibration platform. You see how your device reacts.
How many
to that
components
vibration and shocks.
fell off?
Yeah. If you wanna go deep, you can do mean time between failures prediction. So when you have all your components on the board, you know that each of them can fail, for example, once in 10,000s of cycles. But when you start putting them together, like for your product to work, every component must work. So, and that you multiply that variability. So even though each component is pretty reliable, when you start stacking hundreds of components together, your risk of having product which is not working can be going into single digits of percents. So you really want to, for example, that's especially true with batteries, capacitors. They do specify that, and you want to know this, especially if your product is critical. I was designing a lot of industrial machines before, so that was number one thing that we were cared about. What is our mean time between failures?
I would like to point out, I've seen this many times when a friend of mine, for example, they sell computers and modules, and very often their customers, they ask for these calculations. They would like to see these reports, and so these are calculations, okay? That's what I would like to point out. This is not like physical measurements, but these are calculated. Correct. That
is correct.
Yeah, okay. I just wanted to be sure I didn't say something wrong.
That is correct, Robert, yeah. And last few things is a EMC test. So every product that want to be sold in Europe or in the US must be safe from EMI. So factory is doing tests. Good factory can do preliminary tests in-house before they send it out to the third-party lab, but eventually it's going to go through compliant labs to do your FCC, UL, CE testing. So this is the part where it gets expensive. So some of those tests can run you tens of thousands of dollars each. So you really want to be, the way I structure this, I'm saying, know how you're going to be selling your product. If you sell direct to consumer, you only need to make sure it is safe and do some very minimal testing. For example, FCC must be done. If you're selling through big box retailers, Amazon or others, they're going to be more demanding on they're going to require UL or CE. So this just be, if you can, delay that compliance before you can actually ramp up your volume, that's great, because your costs really stack up quite substantially. You pay for development, you pay for tooling, you pay for factory, and if you also need to stack those testing fees, it might get expensive. Just be aware that they're going to be there. You'll have to pay them at some point. You can just try to delay it a little bit further down the line.
Mm-hmm. Okay, I would like to point out ESD test. Maybe I would like to also add here.
Yes.
And I know in performance, this may be included also in performance, but very often when we design processor boards, we run burn-in tests. So that's something which is not like normal condition, is like very high power condition for a very long time. So you would like to know it's not going to fail, even if it's going to run on this very high power conditions.
Yeah, that's a really good point. Yeah, so testing extreme conditions is great, so you know what to expect. One of the things that you always testing is that your product doesn't catch on fire, even if something is really happening. For example, if we apply 5 times bigger voltage to your input, is it gonna catch on fire? If there is a spark from the outside, like a 5,000 volt spike, that's gonna emit any noise or spark. So it's about fire safety. So the more you can do here, the less lawsuits you're gonna have later on.
And also returns, because sometimes I remember once we were doing ESD test and our board was failing, and we were like, oh, we failed ESD test. But I'm very happy we failed ESD test, because I really don't want to imagine sending out 10,000 pieces and people touching the device and sending them back because one of the chips would be damaged. So
that is correct.
We are doing these tests not because we have to do them, but because they are useful for future.
Really good point.
It could cost a lot of money if people start returning all the products back.
Yeah. So the more time and money you spend here, the less tears and lawsuits and returns you're going to have later on. So a good factory can do a lot of this testing. You can pick and choose. You can always ask their opinion, and good factory doing similar products or already have those. For example, doing environmental tests might be tricky, but if your factory has that thermal chamber already in the facility, they can do it for you in a matter of hours. Same for mechanical vibration. So if you're just trying to do that in your own lab, it's going to be tricky. But since the factory probably already have this one because they've done it previously for other clients, they can use same machinery for you.
We often find someone local to do these tests because it's something what you don't really need every day. But and it's basically cheaper. Just go there for one day at least and run it a couple of days. Vibration maybe for a week or something. I don't know. Environmental chamber. We used to have one in one of the companies where I was working, and it was running all the time, all the time. Okay, I just wanted to point out how useful having this environmental chamber can be. True.
All right, so that's about testing you expect. So another case study, a smart padlock we've done some time ago, and at the DVT stage, the factory has been doing actual machine to test the device. So something pressing the buttons and then pulling the shackle. So it's hard to do it by hand for required number of times. So actually use the machine to do it for you. So automating some of the testing is happening at the DT phase, especially to do that one-time testing before you actually send it to production. As we discussed, environmental is probably the the most useful test you can do, operating it at different temperatures, humidities, different profiles. So if your product is designed to be working at high temperatures, you actually must do this test because this is most useful indication if you're going to be successful.
Yeah, I think the highlight for using this environmental chamber is because if something is running on the edge, on the limits, when you change these temperatures, you will go over these limits and it will fail. So that's why it is useful to have this. I've seen crystals or oscillators failing. I've seen memories failing, Ethernet failings, like number of peripherals failings, just because we, for example, lowered temperature. And lower temperature was even worse than higher temperature. In higher temperature, usually everything fails when it fails. But in lower temperature, I was very surprised.
Especially for batteries, their performance and their capacity drops dramatically. So for that padlock I showed on previous few slides, the battery life was about more than 12 months under like a 25 Celsius under normal conditions, 70 Fahrenheit. But once you put it in the near freezing conditions, it was working for 5 minutes. So, and we had to go through a lot of iterations of selecting the battery, which can actually withstand that lower temperatures. And it still will perform not as good as in normal ambient temperature, but at least you know what to expect and to specify in your requirements.
Exactly. Okay.
Right. Final one is a regulatory testing. So all your EMI is tested in a chamber. So usually
everyone loves these.
It is like a black magic, because it's like you get to the room where it's like a completely nothingness and those antennas. So you do this test in-house first at a factory to get some ballpark number to make sure you spend as little as possible on the compliance, and then you go to the official certified lab. They do it for you. If you can do it in China, it's going to be much cheaper. If you do it in the US or in Europe, it's going to be much more. FCC test can be anywhere from a few thousand somewhere in China to tens of thousands if you do it in the US. And a number of iterations you go, you fail the test, make a change, you go back, you fail the test, you make a change, you pass it. It depends on your level of experience designing those products.
Yeah, I completely agree. So a recommendation or highlight is don't do this certification before actually running some kind of validation test, because it can cost you a lot of money.
True. All right, so hopefully you passed all those tests and you're ready to go to the final validation. It's called PVT, or production validation test. The factory drives the effort here. There is almost no development happening. It's just about making sure the factory knows how to manufacture it at scale. They work with the supply chain, working on every small component. They finalize the tooling on all parts. If it wasn't finalized before, they prepare functional testing. How is it going to be done? How each unit is going to be tested during mass production? They create jigs and fixtures. I have a slide about that. And next, afterwards, they do analysis of how many units actually fail. Because if this is really essential. Let's say your product costs you $100 cost to make. 2% of them fail, and you have to replace them. Your real cost of product is $102 because you have 2% failure. So knowing your yield rate is essential, because that directly affects your cost of goods sold. And at the end of PVT, your factory is usually producing about 10% of your first batch. So if your annual volume is, let's say, 10,000 units, at the PVT stage, they're going to produce around 1,000 units, or 10% of your batch. And final testing must be done at this phase before you start final mass production. You do final compliance testing. And at the end, you have your first commercial, sellable, revenuable units you can actually sell to your clients, to your customers, and to your pre-orders. This is the time when it gets exciting.
This is the time when you realize how difficult it is to sell something.
It's real. It's like, oh man, it's real. Yeah. Yeah. So what factory is doing at this phase? Yeah, they optimize the supply chain. They align your production schedule with lead times. You remember, some of the products might be having like a 52-week lead time, some of them even bigger. That's why it's essential to look at that in advance. So if some of your parts have a 52-week lead time and you only realize this now, your production is going to be 52 weeks later.
Yeah.
So what we recommend doing is, if some of your parts is critical and it's coming with long lead time, you might want to pre-order that part early. So when you come here at the month 15, 16, or whatever that month is, you already have those parts coming to you, and you don't wait another year to get those parts.
Yeah.
Spot buys, when you buy from DigiKey or from local distributors, are acceptable. They might be higher price compared to buying from manufacturer. But if you cannot ship your product, if you don't have that specific part, it's okay to spot buy. Means buying at right here, right now, higher price, and plan your next run with a manufacturer lead time.
Yeah, I don't have any questions today.
Final one is jigs and fixtures. So it's additional layer of work that must be done, is how each board is programmed, how each board is tested. So you do these they call jigs and fixtures. So it's a really inexpensive equipment, but it saves you quite a lot of money in testing. So it should be automated. You press one button, you pull one lever, and the board goes through all the testing, and it gives you pass or fail. The more you can automate, the less you're going to pay per each unit. So this is one of the if you ask what is mass production? Mass production is when a unit comes from the production floor, it goes through the fixture, it gives you pass or fail, and you ship it. That's what's considered to be mass production. If you have to do a lot of manual operation, that's still semi-mass production.
Mm-hmm. And that's what I meant when I mentioned, like when you finish your design or your product design, and then you have to also basically design the test, then
Yes.
This is exactly what I was talking about, because some of these tests, they actually require design another board and write another software. So it's kind of product itself.
Correct.
And higher quantities you deliver, more complex this test is going to be.
Yeah, that is correct. And finally, at the end, you have your first production samples, which can be actually sold. And then, once that is done, the factory can be on its own, manufacturing your product. Mass production, just let me give you a number to keep in the back of your head. Typical expected order quantity per year at the good CM is 1 million product of worth every year. So it means if your product is, for example, bill of materials is $100, they would expect you to manufacture at least 10,000 units of those at a year two, coming up to a total of $1 million of product going for a year. Smaller factories might have a lower MOQ, but the good factories always start with this number. Some of them are even higher. So just when you think that, oh, I'm making 1,000 units of product, which is like $5, just keep in mind that it is good for you. It's good for small factory, but for big manufacturer, it is below the target. Because
I guess they make some kind of percentage from this turnover, and if your turnover is $1,000, they are not going to make any money on it. But it depends, because I know sometimes some manufacturers, they will charge you for time of the people who are doing tests or working or handling your product. So yeah, maybe it
It's usually
depends.
both.
I don't know.
All the cost factory incurs to test, to package, they do charge you that fee, and that's going to be the part of your bill of materials. But the profit, the actual margin is usually charged as a percentage, which can be anywhere from 10% at the high volume up to 20, 30, 40% at the low volume. So if you are paying them $1 million a year for components, the profit margin can be somewhere between 100,000 to 300,000. So that's why they all of them actually they measure how much of your components go through them.
Okay, so they make money on BOM cost.
On the cost of product, it's a good way. It's a transparent way for them to be profitable, to be a beneficiary of your business. So and it's usually a percentage of your entire cost of goods sold. If your FOB frozen board cost is $100, usually it pay them somewhere around 15% markup on top of that.
Okay.
Right. Shipping, so usually ship by sea. You can expect anywhere from 4 to 6 weeks shipping time. It's getting better. In COVID, this was a disaster because the shipping container was costing 3 to 5 times more than it was before. Right now, it's coming back to normal. So right now, you always air ship your first product, like a first batch, but then you try to actually use sea shipping to cost down the cost of your logistics, shipping from China to the US or to Europe.
And customs.
6 weeks.
And duties and VAT and
so if you come up to this phase, congratulations, you officially made it. Right now you have a product in your own country and you can start selling this. Just know that it's never ending process. You will have to do some modifications sometimes some component goes out of stock, you have to replace it, and then there is some quality issues which you have to fix. But congrats, coming all the way to this phase is achievement by itself. And even if it's your first or your 100th product, it's always exciting to see a product. All these months and months of waiting are worth it once you see a product somewhere on a shelf and someone actually using this one. This is an amazing feeling.
I really hope we didn't disappointed some people like, oh, it's so complicated, so much work. No, this is reality.
Yes.
And it had to be explained because this is exactly what I see, that many people who are thinking about making and selling product, they have no idea something like this is happening, and then they very underestimate the cost and time of designing a real product.
Yeah, and just a last comment on the hardware market overview this year. So how the industry is experiencing what's going on. So the semiconductor shortage is still there. Some of the components are still not available, but it's getting better. So supply chain is slightly improving. Trade wars between US and China are definitely picking up. So a lot of our clients actually trying to manufacture their product elsewhere, anywhere by China, ABC. Venture capital slowdown it's harder to raise money for startups. But on the flip side, more money going to deep tech. Hardware is considered to be a deep tech because it's taking more time and actually more resources. So harder to raise money, but if you're able to raise money, if you work on an exciting area, you might be lucky and you might be actually getting some good talent. Conflict in Europe is definitely playing a big uncertainty. A lot of developers who are in Eastern European countries, actually, they have hard time to actually work right now. So it's definitely a big downside for the industry. an entire talent shortage. Surprisingly, after COVID, some people stopped working, some of them changed their roles. So there is a shortage of people. On the flip side, some countries actually are beneficiaries of that. All the talent from Eastern Europe is actually maybe moving to other countries, creating some surplus of talent there. And those countries who never launched any hardware products are seeing some surplus of experienced engineers who can create amazing products.
Okay. So what do you do, or what your company does, and what do you personally do? I think you have slide on this.
Yep. Yeah. A few words about me. I've been an engineer myself for over a decade, developing complex industrial hardware. Think about robotics, CNC machines. I've been doing that for a while. I started AJ Protect in 2014 with the promise of helping startups and small to medium-sized clients to create new products. So essentially, AJ Protect is a product development partner. We help startups and global companies create new products from idea to production.
Mm-hmm.
And we take care of electrical, mechanical, software engineering, supply chain, and all those compliances we discussed on this call. And that's an exciting path, and we're happy to partner with some of the amazing clients and take the ideas to mass production.
May I ask you, where are you originally from?
I was born in Russia.
So
Yes.
so how long are you in California? Since 2014?
Yes, I've been in LA for 9 years. Yes.
9 years. Okay. How do you like, where are you? Los Angeles. Nice weather all year.
Yes, it is, it's pros and cons, there is some downside, upside. Yeah.
I know.
California is a great place to be for tech business.
I miss blue sky every day. I'm currently in Europe. Okay, and what do you have on the next slides? Is there something else? I see there are some nice devices.
Yeah, it was just okay. I wanted to let's record this just that you have it. These are the few examples of the products which you're going to be referring to over the course of this presentation. So this is the AR headset we developed for industrial applications, the night vision, 3D camera, thermal camera. Think about HoloLens. It was actually developed to be a competitor for HoloLens in one of the government contracts. Another one is the industrial headphones for construction workers with active noise cancellation, Bluetooth, intercom radio. One of the first big products we've done as a team. And last one is a Bluetooth smart lock. That uses your smartphone to open and close your lock.
So we have seen some of these.
Yes.
In the slide. Okay. Yes. Thank you very much, Alex. This was interesting, and I really hope this information will help some people and find it useful.
Yeah, it's exciting to share. It's not that much information available online. When I was just getting started, I was trying to let me read it somewhere. Let me try to find a place where I can read all of this. It wasn't available, so it took us a couple of years to gather all the information, and then to present it in this like a 100-slide presentation.
Okay, so thank you very much.
Thanks, Robert. Take care.
Bye.
Bye.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedDevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments, and see you next time. Bye.